So, if I were to make a argument, I would say that competitive inhibition is the most clear and most maybe the simplest because of the fact that whenever you're dealing with an enzyme and catalyzing a reaction, you have something that's kind of binary. It either binds to the substrate or it doesn't. Well, it's actually not quite that simple because an enzyme can also bind to an inhibitor. And with a competitive inhibition, or a model of competitive inhibition, is that the enzyme binds to your inhibitor rather than your substrate. Now, a competitive inhibitor is going to compete with that substrate for that substrate binding site. So in some cases, as is indicated right here with the enzyme succinate dehydrogenase, which naturally is going to take succinate and produce fumarate, well, you have a molecule that's somewhat similar to that in structure, malonate. Well, malonate has two carboxylic acids, just as succinate has two carboxylic acids. However, malonate and succinate are different in that malonate only has 3 carbons, succinate has a grand total of 4 carbons. Now, the difference between them is that malonate will inhibit the reaction from taking place. So it will bind to the same binding site as succinate, but if malonate binds, no reaction is going to take place compared to succinate where a reaction would take place. So malonate is a good example of a competitive inhibitor for succinate dehydrogenase. Okay, now competitive inhibition works by, well, this, as we kind of discussed previously. The competitive inhibitor, I, will either bind to the free enzyme or the substrate will bind to the free enzyme. In the event that the competitive inhibitor binds, well, then you have the formation of this EI complex. Now, a competitive inhibitor reduces the amount of free enzyme available for substrate binding, thus the Km for the substrate is going to increase. Okay, so you can outcompete a competitive inhibitor by adding more and more of the substrate. So basically, the free enzyme is either going to grab onto a substrate or an inhibitor. And if you have an equal amount of each of those two substances, well, then there's almost like a 50-50 chance that that enzyme is going to bind to the substrate over the inhibitor. Now, if you put 10 times as much substrate, or heck, in this example down here, what we have are a total of 6 copies of the substrate compared to 1 copy of the inhibitor. Well, all things equal, that enzyme is more likely to bind. Now, the way that that is all displayed in graphical form is here on the left-hand side, we've got a Michaelis-Menten plot. I'm just going to write an MM. And on the right-hand side of the screen, we've got a Lineweaver-Burke plot. Okay, so a Michaelis-Menten plot, one of the things that's significant, worth noting, is that the Michaelis-Menten plot doesn't really show everything that's going to take place. Because a competitive inhibitor, well, one of the things that it's going to do is it's not going to change, Vmax. Whereas the Km, as we already said, was going to be increased. Okay, so if you really wanted to look at this Michaelis-Menten plot, what's going to happen is it's going to take a bit of time, but ultimately these 3 lines are going to converge and they're going to kind of plateau because that displays your maximum velocity. We've got alpha equals 1, that's no inhibitor, alpha equals 2, alpha equals 3. Those are our different relative concentrations of our inhibitor. Now, a Lineweaver-Burke plot generally is going to show that inhibition a little bit more clearly. It's worth noting some of the points that are going to be the same. For instance, your y-intercept, no change, because, well, what we already said a moment ago, our Vmax is not going to change. However, our Km goes up. Okay, so now when you look at these values right here, this is our initial Km right here, and then these other points are as we increase our Km, what happens? Well, that number gets closer and closer to 0, so it's a little bit counterintuitive, but that's because the Lineweaver-Burke plot is a double reciprocal plot. Double recip plot. Okay, so what we have is that number gets closer and closer to 0, so it goes from, let's say, -3 to -2 to -1 and so on. That Km is increasing even though that x value is decreasing. Okay, so it's important to know what these two graphs look like. Now, this shows us a way to calculate our Ki, and remember our Ki is basically our way of reflecting and evaluating what the affinity that our enzyme has for our inhibitor. So this slide shows us maybe the more effective and easier way to calculate the Ki for your competitive inhibitor. First, what I'm going to show you is the data or example data with no inhibitor present. Our Km for that enzyme substrate combination is 1. Okay, now whenever you have an inhibitor present, which is displayed by our blue line with an inhibitor concentration of 2 millimolar, well, our Km apparent is 2. Okay, so we can use all of this information to calculate our Ki. Now, one thing that we could do is, as is displayed here with our top model, we could either use the Km, or for our bottom model, we could use our slope. Now, based on the information provided in this graph, I'm not going to use my slope, but rather I'm going to use my Km. The reason that I'm doing that is because of the fact that, well, I don't have enough information to clearly calculate my slope. I can look at this graph and say, yes, my slope has increased, but I can't really quantify that very well. So whenever I look at this, I'm calculating my Ki with my Km values. So my Ki is going to be my inhibitor concentration, 2, divided by my Km with my inhibitor, which is 2, over no inhibitor, which is 1, minus 1. Now these are nice round numbers, and that's for good reason. It's supposed to be easy, and it's supposed to be kind of presented this way so that you understand the concept. So that's 2 divided by 1 minus 1. So 2 divided by 1 is going to be 2. And so effectively what we're looking at is 2 over 2 minus 1. So that Ki ultimately is equal to 2 over 1, or 2. Okay, so that's all there is to calculating the Ki of a competitive inhibitor. Hope this was helpful. Thank you very much for watching.